Good evening, everyone. Welcoming you to the second session on this series of molecular dynamics using NAMD and VMD. On the previous session, you have seen how the representations, how you have to select specific regions of proteins, and how to split the protein among the co-crystal ligand and others. This particular series, we are concentrating on protein ligand simulations, ultimately to calculate the binding free energy. So like last time, I already told you I'm choosing an example 1 STP, which has a co-crystal ligand biotin, and it is being binding to streptavidin. So I'm loading this protein and going to split them up, and then today we'll be more focusing on how to generate parameter files as well as topology files for the ligand, how to generate PSF files, and how to solvate the complex, how to merge them. All those things we are going to look today. Few things you have to take care. After performing docking, you can also bring in the complex. Not necessarily you need to bring the complex with the protein and the ligand, because the protein is anyway you're preferring, you mostly would do a rigid docking, so the protein is always rigid, and the ligand is after the docking you will come up with the best poses, a 3D conformation. So basically, when you go for molecular dynamics, you can always prefer getting your PDB directly from the PDB database, and your SDF or MOL2 or PDB-QT or PDB of your ligands poses from the docking softwares. Why I mentioned all these formats? Because different software programs exports the poses in different formats. That's the reason. Ensure you need to have the 3D structure, which is the docked pose. Don't generate any smiles or 2D. It will not fit into the right binding pocket of the protein that you docked. Okay, so keeping all those things in mind, so here one more thing I wanted to specify is that for a complex to generate a topology will be a bit difficult. In that case, what we do is we split them up. We have the ligand separately, or if you don't want to have a complex already saved, so you have a ligand already separated and you have the protein. You have to choose the right chain, remove water molecules, remove if there is any co-crystal ligand already there, everything to be removed and split up, and your chain or the protein part should be clean, and your ligand. So we have to treat both of them separately, generate the PSF files and the formatted PDB files using VMD, and then we use a script to merge them. Of course, in GROMACS also we use to merge topology files manually. So here we can use scripts from VMD. I have already discussed about the different types of scripts which you can download from NAMD and VMD web pages, and then we solvate it. So this is the procedure that we are going to do. So I have already downloaded the 1 STP. So people who are not still aware how to download, you have to go to downloads and click on the PDB, and the best practice is try to generate a folder and you maintain things within that. So I already generated a folder called demo, and I already have it 1 STP, and when I give ls I have the PDB file there. I have already run all these calculations once just to check if everything works fine, because when I'm going live, so I have all those files loaded in old folder, and in order to generate the PSF or parameter files or topology files for my ligands, of course I have used a Charmm GUI ligand generator, which I'll be demonstrating today, and I have downloaded the files from there, that is there in that particular folder. Then I have also used a LigParGen where it generates the parameter files, topology files of plenty of molecular dynamics tools. I'll go through them. So before going through all those things, the first step is for us to split the complex PDB, if it is already a complex, into ligand and the protein separately. That is what we are going to do now. So the first part is we have to load VMD. Keep in mind, if you are using Windows or Mac OS, VMD, ensure that you give administrative rights. Sometimes, since you're installing VMD in Windows in the program files and in Mac in the under the applications folder, there might not be write access. When you're generating the PSF files using or reading the topology files, sometimes permission issues might be there. So for a safer case, if your VMD is giving any error while generating PSF files, try to open it as an administrator in your Windows. If it is in Mac, you can use sudo and give the command to open it. In Linux, anyway, I did not install it as a binary in user local, but I installed it in a normal directory, user directory, and then I defined the alias so that VMD will run as it is. So I'm just giving VMD and ampersand, or you know why I'm giving ampersand, so that I can get access to the shell. But again, I'm just giving VMD and running it. So VMD is open. Don't worry about those errors. It's about some rendering about the graphics, because I reduced it to have a better performance. So first I'm going to file. I have to load my complex, browse, and I load one STP. Why this has directly gone to that directory? Because I opened VMD from the same working directory. If I simply click on VMD in Windows or Mac, it will open from the installed directory. Then you have to manually change the working directory. So it is always better you go to that specific working directory and load or call VMD, so that it will automatically consider the loaded directory as a working directory. And then I'm loading the PDB and load, and you can see the PDB, the same PDB which I used for the last example. Okay, but when you're coming here, I'm going to use slightly different things. So let me show you that. Last time when I'm going for representation, I was using all, rest name, water, and all. Now this time I already told you we do not want water, right? So I wanted to save just the protein and the ligand separately. Last time what we did, we just mentioned chain A. When I mention here chain A, of course the chain A will come, along with that water molecules also will come. And I already told you we do not require water molecules. So what we do, we say, or we mention protein, not water. So I need protein. Of course the co-crystal ligand will not come, and without water. So this is the selection criteria, I would say, right? Now, I hope you can see the water molecule. I'm not sure, but let me show that first. So water, and I will make it as CPK2. So I'll just change. I already told you, you have to make the changes and then do the selected atom. So now you can see the water molecule there. So then I'll create a rep, and then here I will say protein, not water. So here now it will select only the amino acids, that is a protein. But keep in mind, all the chains will be selected. So here I'm aware it's only one chain, that's why I'm giving protein. Otherwise I have to specify chain A, chain B. So I have to choose that. And then I say like here probably van der Waals, and I will say here protein, not water, enter. So now you can see there are small red circles or balls or whatever you call. They are the water molecule, and whatever in van der Waals are the protein amino acids. So they are two separated. So van der Waals, I did not choose water, or just let me give just a protein. Let's see what happens. Anything happened? Let me delete this. Okay, so then I just give protein and without water, and then or I just give chain A. Now you can see water molecule is coming, right? So just protein does not anyway bring in the water molecule, but make sure we do it in the proper way. As I think I don't want to confuse again. So there is a purpose why we use protein, not water, and or just protein or chain A, but ensure that you don't mention chain A, chain B, because water also comes into the picture. So here I will say protein, not water, not water, that I already mentioned. Now if you want rest name btn, which I already know it's btn, so that that is our co-crystal ligand. Okay. So anyway, we explored all these things. I just delete it and delete the rep, and then say create a rep and say all as lines, because just I'm making it so that it will be all visible. Okay, so it's all visible. Now if you if I want to make the display background, go to colors, display background, and white. Great. So enough playing around with colors and stuff. So let me go to the work. So you have to select a 1stp.pdb, click the right button and say save coordinates. Here first I wanted to save my ligand. So I'll say rest name btn. Let's imagine that you already have a ligand as SDF or mol2 file, which is exported from the docking software. Keep in mind, don't bring in multiple ligands, bring one by one for this molecular dynamic simulations. So in that case, you need not to do this splitting, but of course you have to remove all the co-crystal water molecule which is already there in the PDB. If you have already cleaned PDB with you, use that protein file for your simulation. So I just give btn, and then I wanted to save, and I'm saving this as a lig dot pdb. Okay, so that is my ligand, and then I'm saying protein, not water. Of course, even protein itself will not come, but still for best practice. And then here we will rename to protein. Keep in mind, you can give any name. I'm just giving for representative purpose, just for understanding. And I click give OK. I'm done with splitting. Okay, I'll just delete this, delete molecule, and it's gone. Now we have a few more jobs left. So let me check what are the files already we have. So we have basically two files created. One is lig.pdb and protein.pdb. This lig.pdb we have to convert it to mol2 or mol. I personally prefer mol because you can use it either in Charmm GUI, or you can even use it in LigParGen. Mol2 is also fine, but one thing to be taken care very carefully. When you are generating or converting to mol or mol2, or let's say from docking program you have already have mol2 or mol file, you have to ensure the hydrogen, there is no missing hydrogens, the bond order is perfectly all right. If the bond order is having any issues or there is missing hydrogens, generating the PSF files using Charmm GUI or LigParGen will have issues, and they try to assume the bond orders, and that is not good, right? So make sure those things are taken care properly, and it is very, very important that bond orders are not in a guess mode, but you have already been considered it very carefully. So let me run OpenBabel again to convert the file format, but otherwise if you already have the files being in SDF or mol2 or mol, no worries, you can skip this step. So OpenBabel, OBabel, then minus I, I'm defining my input file format, that is PDB. Then I'm defining my input file, that is lig.pdb, and then my output should be in mol file, I mean format, and I'm defining what is my output file. So it should be minus capital O space, I again give lig.mol, and then I add -H. If there is any missing hydrogens, then this will add the hydrogens, right? Of course, the orientations are not taken care, might not be a bit more of deeper protonation step might not be taken care, but yeah, open Babel's, whatever algorithms and science behind it, it adds a hydrogen. And then I enter, one molecule is converted. Now we have to go to browser, and there are two options available. One is you have to go to Charmm GUI, and you can click on this input generator on the top, and you can see a page comes like this. Don't get confused. Please scroll down. You will be able to see where to upload the files and others. Either you can draw the structure. Of course, hydrogen is required. Otherwise, you can visualize them. But I always recommend either load the ligand ID, which is again from the PDB website, and smiles. Again, it depends. So right, so we are not sure, because if you wanted to just simulate or do simulations or minimization just on the ligand, that can be done using smiles, because you don't have a pre-organized conformation which already fits into the binding pocket of your protein. And then you can here at the last option you have mol, mol2 and SDF, right? So I just click on browse, and I load this lig.mol, which I converted using Open Babel, and then I click on upload mol or mol2 or SDF file. Ensure it is only one single structure in those files. I have to click first upload, and then I have to say please check all hydrogens. Click OK. It is processing and it is loaded, and you have to click at the bottom next step, that is search ligand. Click on that. It will take some time, and it will ask you what kind of name or what kind of residue name, 3-letter code you wanted to give. You can give from 3 to 6 characters. Personally, I recommend 3, and by standard everybody uses 3. Of course, you can change. This is what I was telling you, guess bond order from connectivity. If you are not taking care of missing hydrogen atoms, then you will get an error in Charmm GUI in the next step. So then you have to go back, load again, and then enable this guess bond orders from connectivity. So it is very crucial that you do this properly. Otherwise, there'll be issues in generating the topologies. I mean, the parameter files too. So we just gave lig. Here I am sure that because I already added hydrogen, let's see how it goes. And then now I wanted to generate the PDB, of course, with PSF files with a Charm M force field typing. So it's working. I can see it's running. If I have not added hydrogen, there would have been error already. So let's see. Yeah, it's done. It's good. So the computed energy is given, and the topology files are given like RTF, and the parameter files are given like PRM. So using BMD, again using this RTF and PRM, you can generate the PSF files if required. Otherwise, anyway, while performing the molecular dynamics, you need this parameter file to be defined for your ligand. Otherwise, during the minimization, it pops up with error. And you have to click on this download TGZ. It works in all platforms. Ensure that you have 7-zip installed in Windows machine. In Linux and Mac, automatically TGZ can be extracted using command line like tar, gunzip, all those things. Anyway, so you just download and keep it ready. Okay, and the next option is LigParGen. LigParGen is again very handy tool for multiple molecular dynamics engines. Here also they have clearly mentioned structure must include all hydrogen. So adding hydrogen is mandatory. So why to miss it? And also they support either mol or PDB file only. So that's why you know why I used Open Babel to convert it to mol. So because I can use it for both. It's not necessary both to be used. You can check which one is having a better optimization and see because both of them uses a little bit of difference in parameterization. So that's always good to try. And you browse and you again load mol file, open, and then here it's saying molecule optimization iterations. If you have done docking, I would prefer 0, but if you want to correct some a little bit of artifacts or something is there, you can try changing iterations to 1, 2, 3. It depends. Please kindly go through the manual in detail before making the choice there. Now select the charge model. If you are sure that it is a neutral molecule, then you can go for the first option. But if you think that either neutral or charged, it could be, you can choose the second, and you can choose what could be the charge. If it is neutral, just leave it as 0, and then you can press submit molecule. I'm not going too much into the science behind these generate parameter generation through Charmm GUI and LigParGen. Kindly go through the respective papers if you are more interested into it. Now LigParGen has generated the parameter, but the advantage here is you can see here it has generated for plenty of tools. OpenMM, I'm working on OpenMM also using Jupyter Notebook. So once things are done, I'll be coming up with a video for OpenMM also. Then Charmm NAMD, which we are going to use today. GROMACS also, you can generate GROW and top file. PQR, Explorer is also another package. LAMS, again for materials and solid state. Tinga, BOSS MC Pro, Q, even Desmond, which is again free for academics. So, or you can download all into a zip file and load it. So this is again a 2D, 3D visualizer for your structure that is loaded. So LigParGen is able to generate parameters for all possible molecular docking engines. So these are the two options you have. There are more available, but I don't want to confuse with you a lot. These are the two which I have seen many are currently using it. If you think that your compound is much confidential, you don't want to upload online, of course LigParGen has a version where you can install them locally. Kindly go through the instructions, what all things you have to install in order to run the LigParGen locally. And if you go to the LigParGen homepage itself, it has given a link called LigParGen software from command line. You can click on that, you will have all the recommendations. But again, please check with the licensing terms and conditions when you are using for LigParGen, as well as molecular dynamics engines and others as per your category. It could be academic, non-profit, profit-making, commercial, whatever it is. Please respectively check them apart from what the demo that I'm giving here today. Great. So after downloading all these files, I have already these files into this folder. And as I told you, I extracted to these folders. Let me show you the folder, how it looks like. So Charmm GUI, when I downloaded, you can see that these are the two main files I am going to use. One is PDB file and PSF file, which I'm going to use it for NAMD and especially in VMD also. There are other parameter files also like top-par str, ligand drm str, and then if you go to top-par, you have many more other parameters for Charmm 36. I was telling you last time, for lipids, for nano, for proteins, for polymers, different kinds of systems, you have different parameters. So you could see that this folder contains all the parameters. So when you're running parameterization or minimization, you can always direct to this particular folder so that it takes care of or read the parameters. So for lig, it is their PRM and RTF file. These two files can be used when we are minimizing for ligands. But otherwise, currently we are going to use these two files. So what I can do is I will take these two files, copy them, and put it in the folder where I am going to generate all the other files for protein. So right now what I have done is I have generated the PSF and the PDB file for my ligands. Now let's look at the LigParGen also, what is there. So if you go to LigParGen, you can see GROW file. Of course, you know what is that. It's for GROMACS. ITP file, again for GROMACS, right? LMP for LAMPS. and then you have a PQR, then again PRM and RTF for Charmm, or that is NAMD, and then you have for GROMACS also you have top file and many other formats which supports different other packages. So this gives you all different parameterization for different packages, but we could use here for our ligand in Charmm and NAMDs RTF and PRM. If it is for charged, then this QPRM. Anyway, so here anyway from Charmm GUI I'm getting directly the PSF file and PDB file, formatted PDB file, so that is fair enough for me for Ligand to start here. Right now the next job for us to generate the PSF and PDB file for protein. Let's go to do that. Okay, so let me load VMD everything on front. I'm going to browse and load my protein, just the protein, the splitted one, and loaded it. So you can see the protein here very nicely. Great. Now by default you need not to make any changes. You can just go to modeling and say automatic PSF builder, right? And all this topology files will be automatically loaded. And just ensure, if you are loading multiple molecules, ensure that you have chosen the right protein. The output base name will be protein underscore auto PSF. You can leave it like that. By default it is always like that. Whatever your name of the PDB, that will be the first part of the auto PSF and then underscore auto PSF. The first thing is that you have to do is load input files. When you click that, it is loaded. Let's imagine you loaded input files, you generated PSF file and you just simply closed. And again you're loading another protein, again you're trying to do. It will pop up with a warning, because every time after generating the PSF file, you have to reset the auto PSF. Otherwise it will pop up with an error. It's not a serious thing, you have to redo it, that's all. So I have already load input files. I can choose everything protein if I know what is the system is, and then I can guess and split chain using current selection. At the bottom the chains are selected and I could see around 120 as a length, and it's ranging, and it's N terminal and C terminal, and it's telling it's a protein. If there was water molecule, it would have been displayed another one more row. If there was a metal ion, it will display again a third row. So in order to remove those things, I just added only protein. I need only protein. And then I said, I'm going to click create chain. When I'm going to click on create chain, if there is any patches, if there is the IDs or the residue ID will pop up, and you can add a patch, or all those things could be done. But if there is no patch, then it automatically generates the PSF file and a PDB file for your protein. So I just click create chain. So it's here saying no patches were automatically assigned to your molecule. A complete PSF and PDB will be generated. If you would like to add patch and regenerate this place, use add patch button. But of course, I don't want to do that. Okay, and now the structure is complete, and your structure protein underscore auto PSF.pdb and PSF files are generated. And you have to correct guess about the things. Its accuracy cannot be guaranteed. So because that's what you have to be very careful in from the beginning, whatever you are doing. Otherwise, the splitting might not be proper. And click OK, and the PSF file is now generated. For a good practice, once you generated the PSF file, just click on reset auto PSF and close, because next time when you're using, you're proper. Now you have the protein PSF file as well as a protein PDB file, and it will be with auto PSF. Okay, so let me delete all these things. Now let me go to this folder to show you. So we have original protein PDB file and the generated protein auto PSF using auto PSF and PDB file, and then we have the ligands PDB file also available. So these are the 4 important files that is required for us to go. Now let us understand what is the difference between this PSF file and topology file. The topology file is what I was representing here, like what to say, str or parameter file. These are the topology file, or topar, like these files, right? RTF. These are all topology files, parameter files. What is the big difference between a PSF file and a topology file? Hope you remember, even in the VMD, when you go to extensions and uh, modeling and automatic PSF builder, you see here the topology files, right? I'm talking about what is the difference between these topology files and the PSF file which is generated. So PSF means it's a protein structure file, and it contains all the atom or molecular specific information which is needed by a force field. So the typing of force field is being taken care there. So whatever information is required, right? And this also contains a different section, like as you already saw, it will contain atoms, information of bond, information of angles, dihedrals, and also impropers. Improper is to, like, it's a term that is used to maintain the planarity, and also the cross terms. So cross terms and impropers, which we usually see as a pop-up when you do GROMACS topology file generation. I have seen several times when I work on some complex proteins anyway. So this is completely going for PSF file, that is protein structure file. This file is required. So existing PDB file will be converted to a protein structure file in order to additionally add all these parameters. And what is this topology file? This contains all the information needed to convert a list of residue names into a complete PSF structure file. So from a PDB, it has to understand what is the actual residue name, and type the force field, or what kind of force field that we are using, of course Charm 36, and then we try to generate the PSF file. So these are the use of topology file. So this we have to understand. Okay, now those things are done, and now what is the next step? The next step is, as a complex, we have to make it a complex, right? So now these are separate. Ligand is separate and protein is separate. And why we separate it? Because we want to generate the right PSF files, and also its parameterization to be done properly rather than a complex. So that we have done. Now we have to merge it. So I have taken a particular script which is from the internet, as well as from the NAMD website, that is called merge. Let me put it here. It's a simple script which you also can prepare. So merge EPSF TCL. So what it tries to do is, of course, I have already mentioned last time, you have to install TCL SH program in order for this to run, and then you requires a PSF gen also. What you are trying to do is, you are reading both the PSF. One is the protein and the other is the ligand rm.psf. So let's say what the ligand file has been generated. Yeah, so whatever I have downloaded from Charmm GUI, the ligand file name is ligand rm.psf. So whatever the name you have coming up there, you have to give the same name. So you can always edit the script with the name that you have given initially. So first it is reading both the PSF for protein and ligand. Second, it is reading the PDB coordinates. One is, of course, it is from the auto PSF, not from the original PDB split what we have created. And the downloaded ligand rm.pdb. So these two are the coordinates. And then we are writing a new PSF. You can give any name, complex or protlig or whatever name you wanted to give, you can give. And that it generates a new PSF and a protlig. Means it is going to combine the protein PSF as well as the ligand PSF into a single protlig.psf, and protein PDB and the ligand PDB together as protlig.pdb. And once if it is finishes, it comes up with a saying that complex generate. So puts is a TCL command instead of print. Okay, so that is what is the scripting in the TCL using TK console in VMD. So how to run this? And I have already told you in the previous video, you have to go to the command line, and I have already run this, so I am just going to explain what is a command. VMD space dispdev, you are trying to define what kind of visualization you require, whether you want a window or just a text. So you would say I need a text, and I'm defining a file, that is -e means you're defining a file, and the same script I'm telling, merge psf.tcl. If I press enter, it will automatically do some things, and it will tell you that reading the structure. So you can see whatever I asked to read, and then it is writing the PSF file. Finally, it is telling how many atoms, bonds, angles, dihedrals, impropers, and also it also tells you the cross terms. And after writing, it is telling you complex generated. This was a print command I gave. If there is any error, this complex generated command will not come. So this is just to make sure everything worked well. Now we could see there are two new files generated, of course including the log file. The first file is protlig.pdb. The other file is protlig.psf, right? Let us load this to VMD and see how this works. We are almost to the end of the session, okay? So first I will go to file, new molecule. That's where I get this particular window at the bottom, right? And then I'll say browse, and I will load protlig.psf first. And I say OK. Now it is load. Of course, you don't see anything. And to the same load files for .psf, ensure this is there. Don't make a change there. And click browse and then load its corresponding PDB. And load. Now you will see the PDB, right? Hope you remember earlier we were mentioning it as BTN for our ligand. But I hope now you can imagine in Charmm GUI, when we generated, we gave a character name, some 3 character. It was already by default, it was lig. So now your ligand name has changed from BTN to LIG. Let's see how it is. So for that, I will go to representation and I will say bonds. Okay, this is for all anyway. I'm just going to change rest name lig. Now you can see it is lig because the Charmm GUI generated the ligand with the name lig. Let's try with BTN if it is still there. So I want to make this very clear because otherwise you shouldn't get confused at the end. See, there is no BTN now because once I uploaded, I already said it should be lig. One thing you can do is instead of lig, you can replace it with BTN so that throughout your project you will be using the same rest name, right? So those things to be taken care. So whatever name you have given there, that's what is coming here. Okay, and I create, and here I say protein. Okay, I should do this first, right? This is what I always forget. Very bad. Now I will say protein, enter. So now you can see your protein as well as your ligand, right? Perfect. So now it is properly visualized and your ligand is there. I'm not going for surface and labeling and all. That's all. Please check with the previous video, you will get to know. There's a different purpose why I did this now. Now we wanted to solvate our system, right? Because in order to generate our box, we have to define certain criteria. So we will go to model and say or add solvation box. Please keep in mind there is one more option available, but for complex it is not recommended. For example, in the previous step, if you're just doing a protein minimization, let's say a backbone minimization, after you do a model, a homology model, you want to do a backbone stabilization or minimization. Here if you go to option in auto PSF generator, there is something option called as add solvation box and add neutralizing ions. This is a post PSF gen option. You can do that, but in the complex, because here in this case we have to merge both of them together, then only we can bring in. So we cannot do when we did that earlier, right? So when we were generating PSF for protein, so we cannot mix and match there. So but options are there to automate it, right? So now we are doing it separately. So we have a solvate, and then automatically it reads a PSF and the PDB file which we already loaded it. And selection for rotation, we are saying all. Output, we gave a file name solvate. I'll just give another extension because to make sure that it is for the complex protlig, or you can give complex whatever it is. And I'm representing the water as WT with a boundary of 2.4. If you're not sure what could be the box size, you can just say use molecule dimensions. You just click it, automatically the software will calculate and populate the water molecule. And then box padding, how extra you wanted to pad the box, right? So here I will just give 7 7, 7. So minimum is 0, maximum is 7. Of course, don't give 100 and 200. There will be too many water molecules will be loaded and it will slow down your machine. So try to add padding only whatever is required. Okay, and then just click on solve it. Now it will generate new set of files which I will show you. So I'll just I have to load, I want to show you the command line also what will happen. So let me keep this aside so that you can see what is happening, because all the whatever click a button you are doing, all in the behind the commands are being executed by VMD, and it is important that you have to see what is really happening on the back end, and then I will show you the GUI what is happening. Okay, so I click on solve it, and now you can see it is doing a lot of things, and it is saying that around 2294 water molecules are being added. Okay, so now coming here, you can see this now. It is embedded in a box. Solvation box is being completed, right? So earlier days it was being completely on a command line. I think now you can see the box perfectly clear, and the box size, everything can be of course we can extract it automatically, which I will be showing in the next session, because we wanted to know the cell size properly in order as the defined box, because when we're doing minimization, that is very important to put in our script. So there is a script to generate these particular box size, which I will be showing you in the next session. And there is one more which is left is we could also do about ionization, which is we wanted to neutralize the system. So for that we use something called as auto ionize, and this can be also done, and it will generate the ionized form, file. And here you can choose the salt, NaCl, KCl, MgCl, CaCl, ZnCl2, MgCl2 and CaCl2. So NaCl anyway standard we used to define, and you can also automate this to a particular concentration, or you wanted to just neutralize the system. So by default we wanted to mostly neutralize, but if it is specific concentration you have to define that, or if you wanted to use a define, you have to add multiple like Na plus Mg2 plus, you can define how many of them to be done, and then you click on auto ionize. If there is anything to be neutralized, it will get neutralized, otherwise no. So I just clicked on auto ionize. Let's see if there is something. It's finished. Okay, so there is a system net charge after adding ions is also given. So these are the which I will be more talking about in the next session anyway. So today, as of this, that's it. So we solvated the box, and we created the PSF files for both ligand and the protein. In the next session, we will be more talking about how to start our simulation, especially the minimization. Last time I showed you how to run an NAMD, but using these files, we will be discussing how to prepare a config file for the NAMD, and then the simulation. So that's all for today. Thank you so much for listening.